Okay, good morning. It's 11 and we can start, right? Continue. So recording, so you all set, we all set. So where we are and where we will go today. So we will still be in the energy game, right? Changing rules, adjusting rules, and so on. But how did we get up here? So you remember, again, at a certain point we decided, okay, let's try to develop a set of scalar tools, right? I'm just checking if I'm not, to make sure that I'm not muted. Set of scalar tools, because it's easier to work with scalar functions, right? Scalar quantities. And so we grabbed our foundation, right? Newton's second law from our foundation. We massaged it with dot product, and naturally out of the Newton's second law we ended up with what is called work kinetic energy principle, and there naturally we introduced kinetic energy, which is the energy of motion, and we introduced the idea of work done by the force if an object moves from some initial point to the final point. All right, and then we looked deeper at the work side, because forces, we can have different forces, right? There are a wide range of forces, right? Some of them are nice, some of them are not so nice. And some of them nice, and we call them conservative forces, right? And for conservative forces, we can introduce potential energy. And that's what we've done in the previous class. So naturally, from the side of the work kinetic energy principle, where we had the work, we introduce the potential energy. And of course, we need to understand what's the, potential energy, it is an energy of what? Potential energy, it's an energy of interactions, right? Basically, it replaces the force. Force is a vector quantity which describes interactions. Potential energy is a scalar quantity which describes the same interaction. So we can use either force or potential energy. All right, and so what else we introduced? All right, and we just and then of course naturally we also if you don't have a non-conservative forces, naturally out of work kinetic energy principle you can come to the conservation of mechanical energy. If there are non-conservative forces, right? So if forces, some of the forces are not nice in the set of forces acting on this system, then of course you will have what is called like a conservation of energy in the presence of non-conservative forces. And we started looking at one example of systems, a system like that. So we had a block sliding down an incline. So there is a friction. So there is a non-conservative force, right? And so there is an angle of inclination, right? Initial conditions are 0, so the block was released from that point. That's where we positioned the origin. We solved this problem in chapter 1, but we solved this problem using the Newton's second law, using vector approach. And now we decided to solve it using the energy approach, so that we can juxtapose these two methods and see advantages and disadvantages, right? Okay, so we started it, we went to this point. So basically, first we identified all forces, right? And analyzed them. Force of gravity, of course, it is a conservative force. So for any conservative force, potential energy can be introduced, right? And I wrote it on purpose mgh. I don't usually like using h, but in this case, since the y direction is perpendicular to the incline, so using y over here wouldn't be correct. So that's why I switched to h. And h, so again, since we introduced the potential energy, of course, you have to show where is your reference point. But in this case, it's a reference level, right? So you can position it anywhere you want, right? And of course, never attach the reference level to a point which, or some object which moves. Quite often I see students on the solving problems attached to object which next moment will be somewhere else. It's not well-defined place for reference point, right? It's something which is relative to the point, attached to the point which is not going to change its position. Right? Okay, in this case, I decided to position the reference level at the bottom because the whole motion is going to happen above that. So I want to have a positive potential energy. I don't want to deal with negative values, right? Okay, so that's my reference level. And as a result, h is the distance from the reference level to the position of an object. If an object above the reference level, potential energy is positive. If an object below, potential energy is negative. In this case, I don't care where the origin, where my reference frame is. My reference frame is over there. So what? I position my reference level over here, and if object above, potential energy is positive. If object below, potential energy is negative. It has nothing to do with the origin which we picked. Okay, all right. So the reference level is over there. And then, so next force, friction, non-conservative force. I put a set phase. So non-conservative force, we cannot introduce the potential energy. It's impossible, right? And so we will have to just use the formula. We will have to just calculate the work done by that non-conservative force. Then normal force. That force is completely perpendicular to what we do. Basically, it doesn't care because it's perpendicular to the displacement. Work done by the normal force is 0. As a result, it just doesn't play this energy game because it cannot do work. It cannot change anything in this equation. So just forget about that force of constraints. Right? It just keeps the object on the incline. Okay, that's its job. So then, and so we have to use this. If we did not have non-conservative forces, we will just have conservation of mechanical energy, but in the presence of conservative force, we have to use that. Again, if you say you don't remember that, or you hate this for whatever reasons, right? Okay, go and grab a work kinetic energy principle. I saw some students doing homework, they just start from the work kinetic energy principle and everything. We derived this from the work kinetic energy principle. So just get that, calculate all the works done by all the forces, and you will end up with exactly the same answer. Right? Okay, but anyway, so we already derived this, so now let's try to use it. So let's start with delta V. Delta T. Delta T, of course, it's a T final minus T initial. Initial kinetic energy is 0 because the object is released or was released, right? So that is 0, right? So as a result, we'll have 1 over 2 mv squared, and that's our unknown, right? You remember what we want to find? We want to find this velocity at the bottom, at the end of the trip. That's what we need to find. Okay, delta U. Change in the potential energy. Of course, it's a U final minus U initial. Maybe I should say that this is, of course, our final point, and of course, this is our initial point, right? Okay. Final point at the reference level, so the potential energy is 0, right? So the final point, at the final point, potential energy is 0, so we will get, so it will be minus mg, and I will still use h, and h, it's at this distance, right? Okay, maybe I can write it. Of course, h is not given, but for a second, let me introduce it. And of course, h can be written in terms of what? D is given, the total length of the incline, and the angle of inclination is given. So we can easily write that as minus mg, d times sine of that angle, since we want to find the side opposite to the given angle. Right, okay, so this done, okay, this is done. Now work done by the friction force. work done by friction. Of course, it's integral from initial to the final position, F dot dr. I think I used r. Yeah, it's not a big deal. I can use just dx. Okay, so first of all, force, which way I write first? Yeah, let me take care of both at the same time. F equals constant. Then F is anti-parallel to dr. dr downward, F is upward. So dot product is going to give us minus, right? And the F can be taken outside. So I will close my explanation box, so it will be minus F integral from initial to the final dr. Again, basically here it's a dx, because displacement happens in the x direction only. Right, and so F, the value of F, we know from the very beginning, basically mu mg cosine theta, and integral is just the length of the incline, right? So d. So that's the value of the work done by a non-conservative force. Okay, so just now we need to put it all together, right? And so delta t, it's 1 over 2 mv squared, delta u minus mg d sine theta, and is equal to wf minus mu mg d cosine theta. So now we can do this mass distraction, right? Mass goes. G and D can be factored out. Okay, I will move that to that side, so it will be V equals square root of 2. G and D goes outside, G, D, and sine theta minus mu cosine theta. So that seems to be the answer. Let me check. It looks correct. Yeah. But it's better to check it. So that's the answer. Of course, the problem is you've done something like this in your Physics 1 classes, right? And I know that. So now let's compare with example 1. I think it's 1.1. Yeah. All right. Okay, so probably I will use blue, right? So in 1.1 example, yeah, I will have to move to this side. No way. All right, so compare with example 1.1. So where we had, I think we derived x double dot equals to g sine theta minus mu cosine theta, and of course if you integrate it once you will get velocity. Sine theta minus mu cosine theta times t. Okay, and now that's what we got using this approach, and that's what we got in that example. Again, it's a velocity, v, and v here. What's the major difference between this and this? What's the major difference?
What does it do, time?
Yeah. It's correct, time. I would just generalize that. This is the function of time, right? It's a function. This is, all these numbers are given. So it's the value of the velocity at a particular point at the bottom. And that is the function, the history. You can get velocity at any moment of time. At, I don't know, this point, this point, this point, just plug t and you can get velocity at any point. It's a function, and this is the value of the velocity at a particular point. So that's the major difference, right? So as a result, energy approach can lead you to the answer faster most of the time. If your attitude is kind of pragmatic, you just want to get the value of something at a particular point. You don't care how to get there, what happens to the system before that moment of time or after, right? You just want to get the value at a particular point, value of something. Then energy approach is great. But if you're interested in the path, in the history of the system, right, what happens with that parameter throughout the whole motion, it's all lost over here. Right? Your pragmatic attitude kills all that information. In this case, when you use a Newton's second law, everything is there, right? So of course it's better. It's sort of like if you want to go, I don't know, to LA, let's say, for example, right? If you don't care about the flowers along the road, buy a ticket to the plane, fly to that point, or fly to LA. But if you want to see flowers and trees along the road, okay, get a car and drive, right? It will be longer, but you will see much more, and you will experience much more. And the same here, right? So energy approach is great if you have sort of like a pragmatic attitude, right? I want to get this at that point, and I don't care about anything else. Right? So that's the point which I wanted to make, and that's why although examples are reasonably straightforward, right, I don't feel like skipping them. Maybe I should write something about this, and of course, out of this, we can get that velocity easily, right? So first of all, maybe first let me get that, and then I will just write a couple of sentences to summarize what I just said. Right. We can get this, right? So first of all, we will have to integrate it one more time. X is a function of t, so you need to integrate one more time. So it will be gt squared over 2 sine theta minus mu cosine theta, right? So then we know the total distance, so we know the position at the final moment of time. So it will be, right, so if you use x at tf, f stands for final, of course, right? It will be, of course, d, right? So just solve it for tf, you will get the total travel time. Once you know the total travel time, plug it here, and you will get the velocity at that particular final moment of time, right? Of course, straightforward. So from here you can get, maybe I can solve it without writing, so it will be square root of 2d over g sine theta minus mu cosine theta, right? I think that's the travel time. Yeah. And then plug it into the velocity. So x dot at t final. Of course, you will end up with this exactly the same. Of course, it makes sense. Right. So you will get 2gd and sine theta minus mu cosine theta. Right. It's sort of slightly, I squeezed everything, but it's exactly the same. Okay, so, and some conclusions, what I just told you. So I will just copy it from my notes. So energy considerations are powerful if you just want to know the results at a particular point. Right. So, conclusion.
And isn't it so that those collapse nicely into free fall conditions at certain thetas?
Of course, course, if you put theta equals to pi over 2, of course, you will end up with free fall. I don't remember, is it in physics 1 or here? I looked at that limit. I think I did look in the chapter 1, right, at that limit, right? Sometimes I skip that limit if I feel like I need to save a little bit of time. But yeah, of course. If theta equals pi over 2, it will be free fall. Right, energy considerations. Energy consideration. Considerations are powerful. If you just want to know, if you just want to know the results at a particular point, the result at a particular point. But of course you lose the history, in which case you can ignore the details of the motion. Okay, but if you want to know the path or the details along the path, okay, let's say if you want to know the path, the history, the path, the details along the path, you have to use the tools of Newton's law. Right? Basically, yeah, using energy approach here, you cannot get an equation of motion, but it's not, there are exceptions. There are exceptions. Probably next class, we will start discussing one-dimensional systems. And we're going to start applying all these energy tools to one-dimensional system. And for one-dimensional system, in Newtonian formalism, you can still get the equation of motion using energy approach, but only for one-dimensional system. When we get to the Lagrangian formalism in 1.5 chapters, right? No, 2 chapters. When we get to the Lagrangian formalism, yes, that formalism, Lagrangian and Hamiltonian formalisms, they allow us to get equations of motion using energy approaches, using energies. But in the Newtonian formalism, no, unless it's a one-dimensional system. Right, but of course that will be in the future. Lagrangian, still waiting. It's probably one of the major chapters in this course, of course, because you're familiar with this. We're just trying to derive everything, build everything up from the foundation, right? Theoretical approach. But you're familiar with this. But what you're not familiar with, of course, Lagrangian formalism. So now, next one. What's next? So now we know how we can get potential energy out of a force which is conservative. How can we move back? Let's say you have potential energy. How can we get the conservative force? Okay, let's just derive that. Okay, probably I will put a new bullet over here. And I will probably write the title. Sometimes I don't want to write the title so that we can naturally come to some interesting tool and then on. Okay, force as the gradient of potential energy. Yeah. So that will be the new title. Right. force, at least that's how it is stated in the book, as the gradient of potential energy. P, potential energy. Right, and again, so we know how we can get from the force, which is conservative. And of course, we introduce it using an integral. So I just remind, so force is conservative, and of course, using integration, we can introduce potential energy, right? And obviously, so if we want to move in the opposite direction, of course, there will be some kind of differentiation. Right? And now, in order to get the force from the potential energy, so there will be some kind of a derivative. But which derivative? Of course, we need to get that. Okay, I don't feel like writing over there underneath because it's difficult, so I will just move myself to this part of the board. So the first midterm exam is usually after chapter 4, after this chapter. I guess we will spend additional couple of classes on this chapter, right? And that will bring us to somewhere middle of October. And that's when I usually give a first midterm exam. So it will be based on chapter 1. Chapter 2 we skipped. So chapter 1, 3, and 4. And again, when we get closer, then we will discuss the exact day for the exam. Class usually is not that big. It's not like 200 or 300 or 400 students, right? Physics 1, Physics 2. In this case, it's easier to come up with a common date. Okay, so yeah, the title is there. Maybe I also draw a picture over here. So let's say we have some system, a particle which moves along this trajectory. Right. So let's say this is dr, infinitesimally small displacement. Of course, everything is exposed to some force, of course, which must be conservative because we deal with potential energy. So this is position r, that is r plus dr. And let's calculate the work done over this infinitesimally small displacement, right? So work as you move from r, okay, system moves from r to r plus dr, because it will be f dot dr. Okay, we can write in the component, of course, form fx dx plus fy dy plus f sub z dz. Okay, from the other side, since this force is conservative, we know how the work done by the conservative force and the potential energy are related, right? So we derive that. So from the other side, of course, which way I wrote it? Just a second. Yeah, this way. So work equals to, of course, again, from r to r plus dr equals to minus du. Okay, differential of a function. From mathematical point of view, we know how we can write differential, right? Which is the function of x, y, and z. U is a function of x, y, z, r. Right, so we can write it, okay, minus. I will probably keep minuses outside here. So it will be partial derivative of u with respect to x dx plus partial derivative of u with respect to y dy and plus partial derivative of u with respect to z dz, right? Okay, so we have two expressions. So of course it must be correct. It must be correct for any dr. So it must be true for any dx's, any dy's, and any dz's. So it can be only true when fx equals to this with minus, fy equals to that with minus, and so on, right? So, so it must be true when, of course, fx equals to the negative partial derivative of u with respect to x, fy minus negative partial derivative with respect to z, and fz minus partial derivative of u with respect to z. It's kind of tedious writing, right? Okay, but anyway, let's write it in a vector form. Let's write it in a vector form in order to feel really like being annoyed, right, by this form. Okay, so f equals minus x hat. Did I use x or i's? Where is it? Ah, yeah, x hat. Okay. Du over dx minus y prime du over dy. Really annoying, right? Really tedious writing this. Minus z prime d. I'm preparing you emotionally for the next step, natural step. Because writing this, it's... especially if you're a theoretician, right? In old days and everything is done on a piece of paper. It's annoying. So there must be something done with this in order to make life of theoreticians easier. Okay, let me anyway frame it, since nothing wrong with that. It's absolutely correct, but it's emotionally annoying. So mathematicians were nice enough, and they introduced a special hybrid operator, Nabla, or del, right, or grad, in order to make life easier of people, right? So, to make life easier, easier, right? So let's introduce, right? So del equals minus right here. Oh, no. X hat d over dx plus y hat d over dy and plus z hat d over dz. So it's a hybrid operator, right? Yeah, runs on gas and electricity. You know, hybrid because it is a vector, and at the same time it's sort of like it has to obey vector laws because it's a vector, but at the same time it has to obey laws of differentiation because based on derivatives, partial derivatives. Okay, so in order to make, again, life easier of people, so mathematicians introduced this Nabla operator. So I will just use it, I will call it hybrid operator. So it's called del or Nabla or grad. Right. As a result, this relationship can be written much nicer. Right. So f equals negative gradient of u. So we can write f as minus gradient of u, or minus this way. So easier. Much easier to write. So now, since we introduced this Nabla operator, and we will need that in the future, right? So let's write the differential of u using this Nabla operator. Right? It's not sort of like right now logically necessary, right? But since we will need it in the future, let's just digress for a second and write how du can be written using this del. Right. Okay, I will put like a small bullet, sort of like a small digression, not logically connected to the previous one. Right. So let's rewrite du using this hybrid operator. Right? Okay, so du is here. Right, du, okay, let me rewrite it. Du over dx. Dx partial derivative of u with respect to y. Dy and partial derivative of u with respect to z. dz. So where is our del? It's this, right? So it will be del u, gradient of u, and then a gradient of u here, here, here. You take a cross dot product with dr. So dx, dy, dz. Right. So let me show that this gives us, so that's the gradient of u, and of course these guys, that's just dr. So dot product of these two vectors, right? So as a result, we can write so du equals to gradient of u dotted scalar product with dr. Right. So we're going to use it in the future, a couple of spots. So basically, it's a three-dimensional equivalent of the expression which you're familiar from even high school or maybe here calculus. df, one-dimensional case. It's a f prime times dx. Okay, let me write. So it's a three-dimensional analog of, so df equals f prime of x dx. Right, you remember from simple calculus at the beginning of the calculus, right? But of course, this is just a three-dimensional case of that situation. Okay, so now we know how we can move back and forth. From the conservative force, we can get potential energy, no problem, energy of interaction, and then we know how we can get from the potential energy conservative force. Okay, before we start looking at examples, right? Similar examples will be in your homework. Let's go back to the conditions that okay, no, I need to move to this side so that I wouldn't be blocking this. Go back to the conditions that a force must satisfy in order to be called a conservative force. You remember, right? So two conditions. First one, that the force, okay, a force, any force, right? A force must be a function of position only. And the second condition, that if you take any 2 points, completely arbitrary 2 points, and the work done by that force between those 2 points must be path independent. So it means that you can take any path and the work must be the same. And where is the trouble in these two conditions, right? Which needs to be addressed, right? So one part of this one of these conditions needs to be discussed and reformulated, must be reformulated. I'm thinking which part should I erase? Probably I'll go with this and then move to there. Right. Yeah. So which statement, which condition must be reformulated? The second one, look, over there, first of all, you have to pick any 2 points in space. Space is basically infinite, right? Then, between any 2 points, you have to consider all possible paths and prove that work is exactly the same. So brute force, straightforward. I mean, if you do decide to sort of show it straightforward, of course, it's a never-ending work. So because it's an infinite number of points you can pick, of course, infinite number of routes. So you will never be able to finish your proof. So it means that that statement, second statement, must be reformulated. It's in a different form, so that we wouldn't have to consider infinite number of points and infinite number of paths, right? In order to prove that the force is a conservative force. So the second condition must be reformulated. Okay, now let me write what I just told you. Right. And title, so let me call it the second condition, that F be conservative. Let's just address that. The second condition, that F be conservative. That F be conservative. Okay, I described you the problem, but anyway, we need to write something about that. Okay, so the first condition, first, F is a function of R only, function of a position only. It's the first condition, and no troubles with this condition, right? So it doesn't have to be readdressed. And the second condition, the troublemaker. Okay, maybe I will just use my notes. So I will just state the old form of the condition. So for any sign of any, so for any 2 points, work done by F is the same for all paths. For any 2 points, work done by F is the same for all paths. For all paths. And of course, between those 2 points, okay. And again, the problem, right? So let me also write the problem, right? So how can we check the second condition without taking all possible integrals between any 2 points? Right? So the problem is, so how can we check, right, the second condition without W/out, without taking all possible integrals, without taking all possible integrals. Without all possible integrals between any 2 points. It's two infinities, right? Between any 2 points, between, right, any 2 points. Okay, so that's the problem. So we need to reformulate the second condition somehow. Okay, so first of all, let me state the condition, new form of the condition, and then we will prove it. And of course, you know that, right? New form. Basically, if you have a force function, if you take a curl of that force, and if that curl is 0, then that force is conservative. And of course, yeah, the first condition is still there. It must be a function of position only force. Right, so let me write the second condition, new. So new second condition, and then we will prove it. The work, done by the force, let me write it. Done by, okay, a force, whatever force you analyze. Done by the force is independent of the path, is independent of the path if and only if curl equals to 0. Curl of f equals to 0. And of course, yeah, that should be framed. Okay, so now you wouldn't have to consider all possible paths between any 2 points. So let's prove it. So let's take, okay, x, y, and completely 2 arbitrary points. So let's call it point A and point B. And so, of course, force is conservative, right? So force is conservative, and we want to get this condition if the force is conservative. So it means that we are going to assume that F is conservative, and work done by that force is path independent. So using that as the starting point, we need to come to this point, to this condition. Right? So since F is conservative, then work is path independent. So it means that we can take any path. We can take, for example, this one. Let's call it through point C. And now let's take the second path. For example, this one, green, through point D. Right? And of course, work done by that force must be exactly the same, because again, we're assuming that, okay, this is correct, and now out of the second condition, we want to get that. So it means that integral of f dot dr over the path ACB equals to the work done by that force over the path ADB. Okay, just work is the same, path independent. Okay, now let's just manipulate with this. Let's just move this term to the right-hand side. No, left-hand side. And of course, it will be equal to 0, right? So it will be integral. Okay, I will stop writing integrand. Too much to write. I will just write integral and the path. So it will be ACB minus integral over ADB equals. Right? And it equals 0 because I moved to that side. Now, integral, let's just reverse the direction over this green. Why not? It just minus will just appear, nothing else will happen. So we will end up with integral of ACB plus integral of BDA. Just to reverse the direction. Oh, no, not here. Right. Reverse direction. Right. Okay, so now ACB BDA closed loop. So we can write integral over the closed loop AC ACB dA of f dot dr, and it's equals to 0. So it looks like, okay, so the preliminary result. So if the if both conditions are correct, then integral over the closed loop, any closed loop of f dot dr equals to 0. But again, it's still any loop, so it means that you must consider infinite number of possible loops, right, in order to convince somebody that that force is conservative. It's still not what we want. We want to get rid of all these infinite numbers of loops or paths. So we need to dive deeper, right? And we need to recall the Stokes theorem. Okay, I need to move to that part. And for several years, I misspelled the Stokes name. Right, I was teaching it for about maybe 3 years, right? And no one told me, right? So I thought that spelling is correct, and then I think like a couple of years ago, 3 years ago, somebody told me, that's not correct spelling of his name. It's mainly because I took a mathematical analysis not here, right, but in Ukraine. So as a result, I was not familiar with the correct spelling, and I was confident that I was right, so I didn't check. All right. So now let's use Stokes theorem. Oh, what an ugly Stokes. Recall Stokes theorem, right, which connects, you remember calculus, line integral with the surface integral and surface bounded by that integral over a closed loop. Right? Of course, it's a line integral, but integral over a closed loop it connects integral over the closed loop with integration over a surface bounded by that closed loop. Right. Okay, so now let's write it. So integral over a closed loop f. Okay, I will use in our case, f dot dr. Right. Okay, let me just call that loop L equals to the surface integral. Of course, now surface is not closed. Right? It's just bounded by the closed loop, but the surface is not closed. Curl of curl of f dot ds. ds is the area vector, right, perpendicular to the surface. Magnitude equals to the area of that patch ds. Right. Okay, so that's Stokes' theorem, and of course this is the surface, and I will emphasize that surface S, any surface bounded or enclosed, no, bounded by the loop L, right? So, for example, if I have this loop, right, it looks familiar. I took it from the stock room and never returned it, right? So, surface S can be either flat or this baggy type, or even more complicated, or you can any surface, as long as it is bounded by the contour, by this closed loop, right? Probably I should write S is any, and I will emphasize any, it's keyword, any surface bounded by L. Right. Okay, so as a result, of course in calculus you proved it, right? So as a result we can rewrite our statement, and in the new form, right? So integral of f dot dr equals to the integral of curl of f dot ds equals to 0, right? And so now out of this, of course, we're supposed to get the right result, the correct result. But which key words I have to pronounce from the mathematical point of view, from the point of view of calculus? I remember our professors who brutal to us about all these conditions, about proving everything, right? So which words I have to pronounce in order to write that curl of f equals to 0? Okay, I will write. And still, which words do we have to say, except for please be extracted from the integral, right? When we can take this integrand and call it 0. The key word I already underlined, any surface. It means that this ds can be any, right? So for the flat surface, where is my loop? Here. For a flat surface, ds will be perpendicular, right? If it's a baggy type surface, ds can be that way, this way, that way. You can make surface more complicated, and ds can be in all possible directions. Or you can create baggy type surface on this side, right? Again, ds can be in all directions. And for any of those directions, because you have options to pick any surface. So for all those directions of ds, this integral must be equal to 0. So it can be true only if curl of f, this integrand is 0. So because that's why I underline, because that's the key word, any surface. In that case, any ds, and this integral can be 0 all the time for any surface, for any ds, only when the curl equals to 0. Make sense? So let me write it. Okay, since it must be 0 for, and again, I will capitalize for any DS's, and of course any S, right? Any DS, any S, right? Any DS vector, of course DS follows from this, right? Because you can pick any surface bounded by the closed loop. So as a result, curl of f equals 0. And of course now we don't have to consider all possible situations, right? So we passed that we passed that. So now we just analyzing a function. Take a curl, all right? Okay, so now after this we will start looking at examples, because now we know everything, how to deal with potential energy. We know how to find it. No, first, before you can find potential energy, you need to check if your force is conservative. First step, check the force. If the force is conservative, the second step, finding the potential energy, right? And the last step, checking, right, if your potential energy can lead back to your force, right? It's a part which I erased, right? That gradient F equals negative gradient of U. So we will check all those three. We will practice all those three conditions. No, not conditions. Rules, whatever. Right? Tools. All those three sets, three tools. Right, but before, since we will need this curl, so let me write components. Let me write it in a component form, and then I will use it. All right, of course, we will calculate it using x, no, I, okay, I, j, k, d over dx, d over dy, d over dz, and then, of course, fx, fy, fz. All right, and it must be equal to 0. So as a result, x component we can write. Right, so curl of f x component will be dfz over dy, partial derivative of fc over dy, minus partial derivative of fy with respect to z. I will just use only x component, but anyway, let's write all the components. Curl of f y component, it will be with minus, so we can start with that diagonal. So it will be partial derivative of x with respect to z, and minus, no, yeah, it's correct, yeah. And minus partial derivative of fz with respect to x. And z. So dfy over dx and minus partial derivative of x with respect to y. Okay. So, but again, as I said, I will just use the first only component, and then I will write similar. You can get the rest. You can show the rest. Okay, so now we can erase this. In the example, force of gravity, that universal law of gravity. Let's show that it is a conservative force. Get the well-known formula for the potential energy, and then we will check if we can get that conservative force out of the potential energy. Right? And then in your homework there will be some other functions to analyze. First, if it's conservative, and then you will have to find the potential energy and so on in a similar way. So, example. Right. So, force of gravity. So let's just analyze force of gravity. Okay, so probably I will start with the picture. Right. So let's assume that we have two objects. Right. Let's call the first one M capital. The second one, let's call it M small. Coordinate system. Let's introduce the reference frame because we're dealing with the vectors, so we have to be careful. Right. And of course, position vector. Maybe I can, yeah, black is fine. So position vector R. And of course, the force is the central force, so the force acts, it's a force of attraction, of course. It will be this way. And so let's write it, and of course, in a vector form. So it will be force of attraction. So it will be in the negative R direction. So we'll have to write minus G M capital M small over R squared R hat. Too many constants. Let's just hide them for better times. Right. So let me call gamma as minus G M capital M small, close my explanation box. And let's switch from the unit vector R to the position vector. So as a result, I can write F equals to gamma over R to the power of 3 R. Okay, it looks better. And so before I continue, let me write in the component form because I'm going to use Cartesian coordinates. Maybe not the best. Right, so Fx, of course, it will be gamma x squared plus y squared plus z squared to the power of 3 over 2 n times x. Y and z components will be similar, right? So here we just have y, here y, and then z and z. I'm just don't feel like rewriting exactly the same 3 times. Okay, 2 times. And so first part A, show that F is conservative. F is conservative as a first step. Right. So we just need to, of course, look at the curl. Curl of F must be equal to 0. Components, that's why I wrote them. So let's just look at the first component. So curl of F x component equals, so d over dy, z component, so it will be gamma z divided by this quite ugly structure. Right. Oh, it's not the whole story. It's now minus, similar minus d over dz. So now y component, so it will be gamma y and x squared plus y squared plus z squared to the power of 3 over 2. Okay, so let's differentiate. What can be easier than that? Y is only downstairs. So we will get negative 3 over 2. Then we will have to differentiate inside y squared, so it will be 2y upstairs, so we'll get 2y, and this, since it's the partial derivative, so z is basically a constant, gamma z, and the power will increase by 1, so it will be 5/2. So it will be x squared plus y squared plus z squared to the power of 5/2. And this minus, then again, minus 3/2. Now differentiation with respect to z, so 2z will pop up upstairs. So we will get 2z, and gamma and y is treated as a constant, so divided by exactly the same, x squared plus y squared plus z squared to the power of 3/2. All right, and let's look. Yeah, 2 gets cancelled, but it's not a big deal. What we have, negative gamma yz and the same in this denominator r to the power of 5. Here plus 3 gamma yz and the same denominator. Exactly the same, two exactly the same terms. So equals to 0. And similar, you can get y and z component, right? So similar, curl of f in the y component and curl of f z component equals to 0, right? So we conclude that curl of f equals to 0, and of course, conclusion, f is indeed conservative. F is conservative. So part A, now part B. Okay, we convinced that this is the nice force, good one. All right, so now let's calculate the potential energy. At least let's start. Most likely we will have to finish. Or maybe we'll stay a little bit longer. So yeah, I don't need this, I can erase. So part B, so potential energy. Okay, we have a definition. All right, so negative work done by the force as the system moves from the reference point to the point where you want to find the potential energy, right? So by definition, U as a function of r equals minus integral from r naught to r f dot dr, right? So that's definition. Of course, you have freedom to pick any reference point, but so for now, I don't see any reason why we have to move the reference point to a certain point. Of course, you know where the reference point is, but let's get it naturally. Let's see that it makes sense to move the reference point to the point where it is usually, right? So let's assume that the reference point is some arbitrary point. We will find the potential energy, and then in an attempt to simplify it, we will move the reference point to the best possible point, to the best possible place. Okay, probably let me draw the picture. Yeah, probably I should frame it because that's basically a definition, right? And our picture, but now I will make it a little bit bigger. So this is our M. Let's say we want to find potential energy at that point. Again, potential energy, it's an energy of interaction. Of course, there must be at least two objects, right, interacting. If you have a point mass in an empty space, what will be the potential energy? Of course, 0, because there is nothing to interact with. Right, and of course, that's these are, so that's the position where that mass is. Okay, so then, as I said, since we don't know which point is the best for the reference point, let's just pick it somewhere. And I will position my R0 over here. Okay, I can turn coordinate system, and every time I can position R0 on the horizontal line, and just for the sake of convenience, slight convenience. We're not losing any generality. Right. Okay, so that's my reference point. Let me show it with the blue. So that's my R0. So now we need to calculate this work done by this force as we move from this point to that point. And we already proved that the force is conservative, so we can use any path our soul desires, right? So you can go straight, but it doesn't look at that's the best, smartest option, right? The best option would be go first radially to the distance r, like here, and then move around the circle. Of course, circle centered at point M. Right? Okay, so let me show the path. So the best option will be to go to this point and then go around this. It doesn't look like a circle. Right. And then this way. So that's the best path. Again, we can pick any path. R0, first of all, a reference point. And we can use any path. So, as I said, we will pick that one. Which way I label it? A, B, C. Okay, let me label this, right? So this is point A, this is point B, and that's point C. So, of course, this integral must be split into two parts. Right, so as a result, u function of r equals integral from first over AB, and f is here. So now let's use f. So gamma, gamma of, I think I still used r to the power of 3, yeah. So r to the power of 3, then r dot dr. Okay, now, since basically upper limit is r, right, so I can show from r0 to r. So in order to avoid confusions, right, usually, variable of integration, prime is used next to the variable of integration in order to sort of distinguish it from the upper limit. So let's do the same. Prime, prime, prime. Right. And the same for the second path. So from r0 to r, and that's why this time from B to C. Again, gamma over r prime 3 to the power of 3 r prime dotted with dr prime. And so now let's look at AB. Let's start with BC. So what is dr for BC? This is dr, right? And where is r prime? R defines position relative to the origin, right? So that is our r. Okay, let me use primes, r primes. What's the angle between them? 90 degrees, because over here we moved around the circle. So that is tangential direction, that is radial direction. So in this integral is 0. So over here, since r prime is perpendicular, oops. Okay, I'm holding you longer than I thought, perpendicular to dr prime, so that integral is 0. Okay, let's call it a day, right? I will probably start from the very beginning next class, right? Because I thought it would take me like a couple of minutes, but it's already like 5 extra minutes. I'm not in a position like Dr. Egan. Yeah, he can hold students as long as he wants, but because he is Dr. Egan. Right. Okay, guys. Right. So on Thursday, we will just finish this example, and at this point, we can say we've developed all tools for the energy approach, for an energy consideration. So after that, we will start applying them for one-dimensional system as the simplest possible system. And of course, some one-dimensional systems are quite complicated. You will see some of the examples, right? All right, and then there will be some couple of sections kind of not directly kind of related, right? So we will prepare a few things for the future, right? So there will be one class of random stuff, and then oscillations, and then Lagrangian. Beats like a drum. Proudly in the sky, the sun shines like a gold.